Good day, everyone. Today we are going to present a paper titled An Insight into NeuroEvolution and Genetic Algorithms for Text Classification. The authors of this paper are Kevin Kadamala and Dr. Josephine Griffith from the University of Galway, Ireland. First, we're going to give a bit of an introduction to the problem we're dealing with, its challenges, and the goal of the paper. Text classification and natural language processing usually involves classifying or categorizing texts into predefined classes or categories. This has a lot of applications, and some of them include social media analysis, email spam detection, sentiment analysis, intent classification, etc. However, this research field usually requires knowledge of multiple domain areas for a given problem. Text classification in NLP can be of two types. Multi-class, where a document or text can belong to any one class or category, and multi-label, where a document or text can belong to multiple classes or categories. So what are the challenges associated with it? The state-of-the-art text classification systems are now built using artificial neural networks, usually designed over an iterated research process. ANN architectures like the recurrent neural network, the convolution neural network, and until more recently, the transformer have become common in NLP tasks like text classification. Many of the state-of-the-art NLP models now use the transformer architecture in part or as a whole. Hence, the challenge for researchers lies in fine-tuning models for these classification tasks while ensuring that every class is sufficiently represented in the model hypothesis. So, how can we overcome these challenges? Is there a way to skip the fine-tuning step and automate the design of the classification layer? Well, evolutionary computing and neural architecture search could help us achieve this. Hence, in our paper, we evaluate two such neural architecture search techniques. First, the NeuroEvolution of augmenting topologies on the NEAT algorithm, and the second, the genetic algorithms. These algorithms could help us in finding novel architectures that could at least perform as well as human-designed ANNs or artificial neural networks, but without the human effort of fine-tuning. So the goal of our paper is to better understand how NEAT and JAs work and help in the task of building better artificial neural networks, and to then present and analyze the results of the two classification tasks to understand the applications and performance of evolutionary computing techniques in natural language processing. We now come to our methodology. The datasets used in our work include the Reuters 21578 dataset and the 20 newsgroups dataset. The Reuters 21578 is a multi-label classification task dataset. It consists of news articles classified into 90 different topics. One of the features of this dataset is the interlabel dependency amongst them. For example, labels like barley, corn, rice, oilseed, wheat, etc. The label grain is often included. The 20 newsgroups, on the other hand, is a multi-class classification task dataset. It consists of newsgroups posts organized into 20 different topics. The training and testing sets are split based on messages posted before and after a specific date. In our work, these text data are passed through the BERT mini model to generate text embeddings, which are then used as inputs for the two algorithms that we'll be explaining in the next slide. This brings us to our first algorithm, the genetic algorithms with gradient descent. Genetic algorithms consist of a population of individuals that represents a solution. Each individual or phenotype has a set of properties known as chromosomes or genotype that can be altered and mutated. The figure you see in front of you shows an example of the genotype with its genes and the representative phenotype as a feed-forward neural network. Each gene is represented by a list of size 4 that contains the layer type, the activation, the number of output features, and the kernel size, respectively. The possible layers include convolution, pooling, linear layers, and other layers like LSTM, GRU, and normalization layers. Activations include soft plus, ReLU, leaky ReLU, tanh, and sigmoid. Now, this information is not always going to be used by all the layers. For example, you can see that pooling and normalization layers do not use any activation. GRU layers do not make use of the kernel size, while if you can see the convolution layer makes use of activation, the hidden size, and the kernel size. So each layer has access to all of this information, but the information is used based on the layer's constraints and criteria. The last two layers of any neural network will always consist of a flattened layer to flatten the outputs into a single vector and a linear layer with the output shape equal to the number of classes. For a multi-label problem, a sigmoid activation is added at the end. A population will then contain multiple individuals or networks where they will be trained for a certain number of epochs. The network weights for each individual are optimized using gradient descent. Early stopping is also implemented to efficiently use training resources and prevent overfitting. A small subset of the training data is used as the validation set to monitor this early stopping algorithm. Once the network has been trained, its fitness will be calculated on the validation set. Then the genetic operators like selection, crossover, and mutation will be applied to generate a new population of genomes or networks for the next generation based on these fitness values. We now come to our second algorithm known as the NeuroEvolution of augmenting topologies, or the NEAT algorithm. The NEAT algorithm, we use two variants of the NEAT algorithm. The first being the original or vanilla NEAT, and the second being the error correcting output codes, or ECOC NEAT. The genome in the original NEAT consists of the node genes and connection genes, where node genes has information like whether it's input or a hidden node or an output node, while the connection genes represents the connection between these nodes in the neural network. The ECOC NEAT is a variation of the NEAT algorithm that implements class binarization along with NEAT. To solve the multi-class problem, ECOC combines many binary classifiers. In our case, these binary classifiers are learnt with the help of the NEAT algorithm. We implement a similar implementation that as we see in scikit-learn, where it includes a code size as a hyperparameter used to create a code book. Then we train one binary classifier per bit in the code book using NEAT. The inputs are then passed to each classifier to generate predictions, where the positive class's prediction probabilities are used to find the closest class in the code book. So from the figure, we can see that multiple binary classifiers are learned, and their outputs are then matched with the closest class in the code book using Euclidean distance. This brings us to our results. Each algorithm has been run thrice, where we report its results with its mean and standard deviation values. For the Reuters 2178 dataset, we see that while neural networks trained through the GAGD algorithm demonstrate competitive performance compared to the current state-of-the-art models, NEAT cannot really evolve neural networks that can compete with such models. We've tried two variations of the GAGD algorithm where we include activations in one and we exclude them in another. And even while the results are not too drastically different, using activations just does perform slightly better than ignoring activations completely. If you recall previously, the 20 newsgroups dataset is a multi-class dataset. Hence, we could even evaluate ECOC need. Neither vanilla nor ECOC need, however, has been able to produce competitive results. On the other hand, the GAGD can evolve competitive neural networks, but graph convolution networks still perform significantly better. As you can see, similar to the previous dataset, we evaluated GAGD with and without activations. And we found that including activations, like previously, does perform slightly better than simply ignoring them. ECOC need in literature has shown to outperform vanilla need for multi-class datasets. However, for this dataset, using the original implementation of need outperforms ECOC need, even though in general the need doesn't perform as well as GAGD. So what have we learned from our experiments? With respect to the need algorithm, prior work involved creating their own representation for text data or working on toy datasets. However, the datasets used in our work present a much more difficult learning problem. We believe that the embeddings obtained from the BERT mini model make it difficult for the need to evolve any meaningful architectures. Thus, an experimental setup using previous approaches that relied on vector embeddings from a large language model failed in this scenario. From previous literature, we know that BERT embeddings have been used for fine-tuning to achieve state-of-the-art performance on the two datasets. From the figure on the right, we can see two examples of the neural networks generated by the GAGD algorithm for the 20 newsgroups dataset and the Reuters 21578 datasets. These networks generated are simple sequential models, and they might not be well suited for these tasks. Still, by extending the approach from Anderson et al., it enabled us to evolve competitive neural network architectures. Evolutionary computation can evolve architectures to produce baseline models that can match the performance of human-designed ANNs. Hence, we could use these models as building blocks to build better models with the help of expert knowledge. So what are the conclusions and what is the scope for the future? Our results showed that simplistic neural network architectures evolved by genetic algorithms can act as baselines or building blocks that can be better with expert knowledge. We also showed that needs struggled to evolve competitive architectures, which could be due to the high dimensional space of the BERT embeddings and the difficulty of the text classification problem with respect to the datasets. When comparing the GAGD to NEAT, our results show that using genetic algorithms to evolve ANN architectures with gradient descent significantly outperforms ANNs generated by the NEAT algorithm. This is also true for class binarization methods, but they did not outperform the original NEAT implementation for text classification. For future work, experimenting with other class binarization methods as presented by McDonald et al. Could be worthwhile. The complexity of the architectures generated could be increased by introducing the ability to skip layers or combine the output of different layers into a single layer. Other options to increase complexity could involve increasing the maximum number of layers or increasing the output feature range, which could potentially lead to the evolution of better neural networks. This brings us to the end of our paper presentation. Thank you.